Welcome back to the podcast. Today, we are looking at something deceptively simple, the speed at which you eat. In our modern, high-velocity world, lunch is often inhaled at a desk or devoured in the car. We treat fueling our bodies like a pit stop in Formula One racing. But here is the biological reality. Your digestive system operates on a delay. There is a profound mismatch between the speed of your fork and the speed of your neurochemistry. Understanding this lag time is the key to unlocking better metabolic health. Let's get specific about the numbers. It takes approximately 20 minutes for your gut to send a convincing message to your brain that you are full. 20 minutes. If you finish a large meal in 5 minutes, you have a 15-minute window where you are physiologically satiated, but psychologically voracious. You keep eating because the data hasn't reached the command center yet. It is like sending an email with a really slow attachment. The message is sent, but the inbox is still empty. By the time the "I'm full" notification dings in your brain, you have likely overeaten significantly. The process begins the moment you take a bite. Chewing, or mastication, isn't just about breaking food down into swallowable distinct pieces. It is a signaling mechanism. As your teeth grind the food, you are increasing the surface area for enzymes, but you are also stimulating the taste receptors on your tongue. These receptors send the initial incoming signal to the brainstem. However, the heavy lifting of satiety signaling happens lower down. When food hits the stomach walls stretch. This activates mechanoreceptors, nerves that specifically detect physical expansion. They are the first line of defense against overeating. To understand fullness, we have to understand hunger. The primary driver here is a hormone called ghrelin. Produced in the stomach, ghrelin levels spike before a meal, screaming at the hypothalamus to find food. As you begin to eat and the stomach stretches, ghrelin production is suppressed. But this suppression isn't instant, it is a gradual fade-out. If you eat rapidly, ghrelin levels remain high for the duration of the meal. You are effectively eating while your body is still chemically screaming that it is starving. Eating slowly allows ghrelin to taper off while you are still midway through the plate. Once food passes from the stomach into the small intestine, the chemical conversation gets more sophisticated. The intestines release a peptide hormone called cholecystokinin, or CCK. This is a crucial satiety signal. CCK is released specifically in response to fats and proteins. It tells the stomach to slow down its emptying rate and signals the brain to terminate the meal. But again, the release of CCK relies on the presence of partially digested nutrients in the intestine. If you rush, the nutrients haven't arrived there yet, and CCK remains dormant while you reach for seconds. As digestion progresses, we meet the heavy hitters of satiety, GLP-1 and peptide YY. You might recognize GLP-1 from recent news about weight loss drugs, but your body produces it naturally. These hormones are secreted by the L cells in the lower intestines. They dramatically inhibit appetite and enhance insulin secretion. They are the body's way of saying, "We have enough energy now." The catch? These signals are released later in the digestive timeline. Fast eaters often finish their entire caloric intake before these powerful hormones even begin their work, completely bypassing the body's natural braking system. All these chemical signals, from the stomach stretch, the CCK, the GLP-1, need a transmission line to the brain. That line is the vagus nerve. It is the superhighway connecting your gut and your brain. The vagus nerve integrates all this noisy data into a coherent signal of satiety. However, nerve transmission speed is finite, and the integration of chemical signals takes time. It is not a fiber optic cable. It is a complex biological feedback loop. When we eat mindfully, we align the pace of our intake with the transmission speed of the vagus nerve. Finally, all these signals arrive at the hypothalamus, specifically the arcuate nucleus. This is the brain's air traffic control for metabolism. It weighs the suppression of hunger against the stimulation of satiety. If the signals arrive gradually, the hypothalamus can gently dial down your appetite. You feel a pleasant sense of fullness. If the data comes in a massive delayed dump because you ate a burger in 3 minutes, the hypothalamus gets confused. It might signal nausea or extreme lethargy, the dreaded food coma, instead of comfortable satisfaction. Timing dictates the quality of the feeling. There is also a psychological component called sensory-specific satiety. As you eat a specific food, the pleasure you derive from it decreases over time. The first bite of steak is heaven. The 20th is just food. This decline in palatability helps you stop eating. When you eat quickly, you override this sensory decline. You shovel food in so fast that you don't notice the pleasure dropping off. By slowing down, you maximize the enjoyment of the first few bites and actually notice when the food becomes less interesting, naturally prompting you to stop sooner.
Let's talk about insulin. Eating slowly doesn't just help you eat less, it changes how your body processes what you eat. Rapid eating causes steeper spikes in blood glucose. This forces the pancreas to pump out massive amounts of insulin quickly to manage the sugar rush. Over time, these violent spikes can contribute to insulin resistance. When you eat slowly, glucose enters the bloodstream at a more moderate, manageable pace. You are essentially giving your metabolism a steady stream of fuel rather than a flood, which is far healthier for your long-term metabolic function.
So, how do we hack this biology? One simple tool is hydration. Drinking water between bites does two things. Mechanically, it adds volume to the stomach, triggering those stretch receptors we talked about earlier without adding calories. Temporally, it forces a pause. You cannot chew and drink simultaneously. By taking a sip of water every few bites, you are physically enforcing a rhythm that matches your hormonal clock. It acts as a punctuation mark in your meal, giving your gut hormones the precious seconds they need to travel up the vagus nerve.
The texture of your food matters immensely. Ultra-processed foods are often engineered to be soft and easily swallowed. Think of white bread or fast food burgers. They require very little chewing, which encourages rapid consumption. Whole foods, crunchy vegetables, dense proteins, fibrous grains, demand mastication. They force you to slow down. You physically cannot inhale a raw carrot the way you can a French fry. Choosing foods that require mechanical effort is a passive way to ensure you are respecting the 20-minute rule without even looking at a clock.
Here is a practical drill for your next meal. The fork drop. It sounds trivial, but it is neurologically profound. Most of us load the next bite onto our fork while we are still chewing the previous one. This is an assembly line mentality. Try this. Put a bite in your mouth and physically set the fork down on the table. Do not pick it up again until you have swallowed. This breaks the cycle of automatic eating. It forces you to engage with the chewing process and buys you time for CCK and GLP-1 to do their job.
Eating is also a social signaling system. Historically, we ate around fires, sharing stories. Conversation is a natural break on consumption. If you are talking, you aren't chewing. Studies show that people who eat socially tend to eat more slowly, provided the environment isn't chaotic. However, if you are eating alone, you lose this social regulator. If you must eat alone, avoid screens. Scrolling through social media mimics the dopamine hit of food, distracting you from satiety signals. Turn off the TV, put down the phone, and engage with the meal itself.